This is the video based off the post lab for the disturbing equilibrium. For number 1A, it says how does the direction of shift relate to the side of the chemical equation? The heat term is written when the sample is heated. So what it's basically asking is how does the shifting of the equation relate to the heat that's in an equation when the reaction is heated. So let's take a look at the reaction that we have in our lab packet. N2O4 plus heat gives you two NO2s, and this is red, and this is colorless. So in this case, it might be best to look at this equation as though it were a balance, where at this moment in time, the reverse reaction going this way and the forward reaction going that way are in perfect balance with one another. So what it's asking is, what would happen if you add heat? Well, the reaction is going to want to go back to equilibrium. So if you were to think of it as though it were a balance, that left side with the heat would weigh more. So the reaction would want to go to the right, proceed to the right, so that way it can come back into balance. So it would want to make this go higher. And in your experiment, you should have noticed that when you did heat N2O4, which was colorless, it did end up getting red. And that was what the demo was at the beginning of the lab. For letter B, it's basically saying what would happen if instead of adding heat, you were to remove heat. So same situation, you have a balance, and right now it's balanced on either side, but this left side, it were to go down, well, it would want to level itself out. So in order to do that, the reaction would proceed this way to be able to balance the reaction. So as you cooled or removed heat from the NO2, you would notice that it would become more and more colorless. For letter C, when it says to write a general rule, we can write it out as A plus heat gives you B. Well, if the heat gets more, then the left side of the equation is tilting towards it. Well, it would want to balance by having the reaction go this way. Now, if you were to remove the heat, the reaction would tilt towards the right, and because it wants to get back to equilibrium, the reaction would go that way. For number 2, it's basically asking the same question, but instead of worrying about the heat, we're worried about the chemical on the side with the heat. So in this case, if we're thinking about A, it would be much the same, that if you raised it, the amount, the equation would be tilted to the left, and to achieve equilibrium, it would want to tilt back to the right, or send the reaction to the right. And if you were to remove A, well, it would want to tilt the reaction to the left, so that way it could come back to reach equilibrium. For number 3, it was basically answered, the second part. When A is decreased, it would go to the side that A is on to make up for that K equilibrium. For number 4, writing a general rule to cover all types of disturbances, you should start seeing a general pattern that when the disturbance affects the side with either the temperature or the concentration in such a way that that side has more of it, then the reaction would proceed to the other side to balance out the equation, much like a seesaw. And if it were to remove the temperature or concentration, well, the seesaw would tilt towards that side to make up for what was lost and go back to equilibrium. For number 1 on the back side of the sheet, what can be said about the rate of reaction of the forward and reverse at equilibrium? Well, at equilibrium, the rates are equal to one another, the denominator and the numerator, and K equilibrium would be equal to 1. For number 2, explain why no visible changes can be observed when a system is at equilibrium, and explain this in terms of rates of reaction. Well, we can explain this in the sense that the change which occurs, well, the change occurs because one or the other side of the reaction itself, either going forward or reverse, is favored, because that's what a reaction is. When the reaction is in equilibrium, they're basically canceling each other out. So that's why there's no visible change when the system is at equilibrium, because what we know as visible change is basically a reaction being favored in either the forward or the reverse manner. But at equilibrium, both the forward and the reverse are equal to one another, so they cancel out one another. For number 3, are the rates of both the forward and reverse reactions still equal after the equilibrium is disturbed? And support it with the observations made. Well, the answer is no, because you notice some change, whether it was going to be colorless or get to a different color, which means that one or the other side of that reaction, one or the other direction of that reaction, forward or reverse, ended up being favored. So as soon as the equilibrium was disturbed, one of the forward or the reverse reactions ended up getting more likely to happen. For number 4, when it says which direction of shift would you observe if only the rate of the reverse reaction is increased. So if the reverse is going to the left and it's increased, it's going to the left. For B, if the rate of the forward is decreased, you're saying pretty much the same thing, that the left or the reverse is more likely to happen now. And then for C, the rate of the reverse is decreased. Well, now the forward is more likely to happen. For number 5, we have a particular reaction. And for A, it says, would pressure change this equilibrium? Pressure is one of the things that affects equilibrium, because if you were to raise pressure, well, the equilibrium would want to, based off of Le Chatelier's principle, it would want to go down. And by going down, what we mean is pressure is related to the number of particles and how they bounce off of one another. So in this case, if we were to look at this reaction, on the left side we have 4 particles, 3 and 1, and on the right side we have 2, and if you count the heat, even then you have 3. Well, let's just count the NH3, which is 2 particles. So if you change the pressure, let's say the pressure goes up, well, now this system would want to equalize and have the pressure go down, and the way you can do that is go to the side of the reaction which has less particles. In this case, to this way. And inversely, if you were to decrease the pressure, it would want to equalize again and go to the side that has more particles, so that way they can bounce off of each other and come back to the place where they were before. So in that case, it would want to go to the left. And then for B, it says to list 4 ways to increase the amount of ammonia, which is the NH3, in this equilibrium. Well, there's a bunch of different things that we can do. We can remove heat. By doing that, the balance would be off and it would want to move to the right. We can remove NH3, same thing, the balance would be off and it would tilt back to the right. We can add H2, so that way we can make the left side heavy, and then it'll want to go back to the right by creating more NH3. And we can add N2, and it's the same thing. And that seesaw analogy, it would tilt to the left and then it would want to go to the right. For number 6, assume that you add water to an ionic solid and it dissolves. What you have is AB as a solid plus heat, giving up or ending up becoming ions of A and B. List 2 disruptions that could get the solid to dissolve more completely. So we should see that here's the solid, and by dissolve what we mean is going this way to its component ions. It's a dissolution of A and B, or AB, the molecule rather. So 2 disruptions that could do that is by adding heat. We would get that seesaw tilted to the left and then it would want to come back to the right. Or we could add more AB. Once again, we would tilt it to the left and then it would come back to the right.